Okay, so this is lesson number 26, the last actual lesson. It's posted on June 5th. Homework for this is due June 8th on Monday. So you got a kind of short turnaround. Also on Monday is a quiz number 4. And then the final is on Wednesday. I'll talk more about this in a separate video, but note that there's special office hours times, there's SI, there's a lot of stuff. There's a review that will be posted on Monday morning. A lot of things available to get you ready for the test. One thing I want to talk about as far as grades, June 8th is the last time for you to switch to credit, no credit. You can go to this link. It's also on Blackboard, and check it out and look at that policy. And if it's right for you, you do it. June 9th to 30th, you'll have to do a petition. So if you want to do it by Monday, June 8th. All right, grades will be posted by Tuesday, June 16th. You should be checking now for any discrepancies. Hey, you don't include this. Hey, blah, blah, blah. Let me know now, because I'll post them and I'll say, hey, look it over. But if you find discrepancies now, that's better. Okay, so a couple other things. There's a survey that will be set up to help improve the class. And then there's SOTIs, which is the official thing. You've gotten emails about that. So please help us out to improve. One other thing, when you get past this class is basically the start of chemistry, right? Most of you will want to move on to organic chemistry. That's Chem 20, or I don't even know what it's called anymore, but it's Organic Chemistry 1. You're going to need all this stuff. Stoichiometry, bonding, molarity, all this stuff, acids and bases, all this stuff is there. We didn't just teach general chemistry just to forget it. It's going to come up. The first month of class is all about Lewis dot structures. So I would suggest study some of that over the summer, take a break and then go back and look over that stuff. That way you're ready to go. All right, if you need to retake Chem 216 over the summer, we don't have it here. You could possibly try a junior college. In the fall, it will be called Chem 2200. Realize that this didn't work this time. So what do you need to do to change to help that out, right? Just switching professors, not going to be enough, okay? All right, so let's move on and let's talk about electrochemistry. This is the last topic we're going to talk about, and this is a special type of reaction, and it's important because this is how we get electricity. All right, and so what we have to do is we need to think back to Chem 215. In Chem 215, we talked about redox reactions. Redox reactions are reactions involving transfer of electrons, right? This is where we get the term electricity from. We can have oxidation, which is losing electrons, and reduction equals gaining electrons, okay? We had some oxidation number rules. So the rule is that you have these rules to figure out oxidation number, and you can see based on that whether it's gaining or losing electrons. For this topic, these number 2 and 3 are key ones, right? Oxidation number for an atom in its elemental substance, so by itself, it's 0. The oxidation number for a monoatomic anion, like Na+, is just equal to its charge. So this has an oxidation number of +1. All right, why does this matter? Well, aqueous redox reactions such as this, if I put a copper wire into something that has silver, I can actually form some solid silver, and the copper is going to go into solution. This type of aqueous reaction that involves transfer electrons, we can use this for electricity. All right, so let's remember what's happening. We have what are called half reactions. If I look at the copper alone, it's going from copper to copper 2+. So what has to happen there? It has to lose 2 electrons. This is called oxidation. Silver goes to Ag plus goes to Ag. This needs to gain electrons. This is called reduction. Reduction involves gaining electrons. Oxidation is losing electrons. All right, so what can we do? Well, we can basically separate these two things into different containers, and then we're going to have electrons going from the copper to the silver, and that's the basis for electricity. All right, so this is what's called a voltaic cell or a galvanic cell. A voltaic cell is a device capable of generating electrical energy from redox reactions. Okay, this happens in batteries, hydrogen fuel cells, etc. All right, so this is an example of it. We'll look at it later in bits. But basically, I have one side of it. There I have the copper, one side where I have the silver. Right? Here's my oxidation, here's my reduction. And I have them joined together by a wire, and this is where my electrons go. All right, so it all starts off by taking the two half reactions and basically separating them. So on one side, we're going to have solid copper and a solution containing copper 2+. Okay? This is called an electrode. An electrode is a solid metal that allows for electricity flow. We submerge it in electrolytes. Electrolytes is just a fancy name for ions. Remember, ion means it is charged. Okay, so there's my copper. On the other side, I have my silver in a silver plus solution. Okay, so here the copper loses 2 electrons. Here the silver gains 2 electrons if it wants to go to silver. But these two things aren't just going to happen by themselves. All right, so remember we said that copper is being oxidized. So the electrode where oxidation occurs, we call the anode. We call it the anode because it becomes negative. The reason it becomes negative is, notice the copper is losing electrons. So those electrons cause this electrode to be negative. The cathode has to lose electrons lose electrons in order for it to go from Ag plus to Ag. So this side will be positive. We call that the cathode. I remember this because anode, N for negative, and it has a vowel at the beginning, and so oxidation occurs there. Cathode has a positive, and it's where reduction occurs. Okay, so I have my anode, my cathode, and what do? I run a wire between them. And this wire allows electrons to go from the copper to the silver. Okay, this right now is what we call an open circuit, though. Notice electrons could move this way, but they're not going to, because what we'd eventually get is all the electrons on this side. That's not going to happen. We need to close the circuit somehow. So how do we close the circuit? We add in something called a salt bridge. So a salt bridge is an inert salt, like let's say sodium nitrate, that's in there. And so what's going to happen is electrons are going to move from the anode to the cathode. Remember, from anode to cathode. And meanwhile, ions are going to move through this salt bridge to even out the charge. Okay. There's one other thing I should mention, and I forgot to. Notice we have copper 2+ and we have silver plus here. Well, we can't have positive ions by themselves. So we have to have some type of anion there also. So NO3- could be an example, right? So we'd have copper nitrate here and silver nitrate there, okay? All right, so anode, so as electrons move, right, the copper is going to become copper 2+. Okay? So what that means is I'm going to lose some of my solid copper, okay? So my copper is going to lose mass. Meanwhile, my silver on this side, the Ag plus becomes silver. So that means that it's going to gain size, right? So I have copper becoming copper plus. That the extra electrons flow to this side, where that allows the Ag plus to become silver. This is that example that we showed at the very beginning, right? Where we basically have this setup with two containers, a salt bridge, and a wire between them. All right, now electrons move across this. And so because there are these electrons and electrons have a charge, we end up with what's called a voltage. A voltage is the energy per charge flowing through this wire, okay? And it has units of joules per coulomb, or just volt. And we use capital V to show volt. Okay, so depending on the metals connected, in this case it's copper and silver, we're going to get a certain amount of voltage. And this is called the cell potential. We call this a capital E cell. Okay, that's the cell potential. That's the voltage that occurs, or that gets produced, when I connect this anode over here to this cathode on this side. All right, so cell potential has units of volts. And if we add standard conditions, remember standard conditions are 1 molar or 1 atmosphere if I'm talking about gases. We would call this a standard cell potential. Okay, if it's not under standard conditions, we just say it's E cell. Okay. All right, so this is a voltaic cell. Okay, we have our oxidation occurring over here, so this is my anode. I have my reduction occurring over here, so this is my cathode. Oops, my H is very ugly there. All right, well, we can't just draw this out, so we end up with having something called cell notation. Cell notation is a way to signify this voltaic cell in shorthand, okay? So what we're going to do is we're going to start off with our anode, okay, over here. And we're going to write the chemical reaction, that's copper going to copper 2+. But instead of using an arrow, we just use a line between them, okay? So I have copper going to copper 2+ on the anode side. I add in states. I can add in other information if I want. Then I have the cathode. At the cathode, I have silver plus going to silver. So I just put that as Ag plus aqueous. A line to signify the reaction going to Ag solid. And I signify that salt bridge, because that salt bridge is needed for this voltaic cell to occur. We signify this by a double line. All right, so I have copper solid going to copper 2+, a double line representing the salt bridge, and then Ag plus going to Ag. This is my anode. This is my cathode. Anode is where oxidation occurs. Cathode is where reduction occurs. Okay, now this cell notation, I can add in some other information. So let's say I wanted to know that the concentration of the copper 2+ over here was 1 molar, or that the Ag plus is 1 molar. I would add this here. And all of these things are going to change the cell potential that I get right here. Okay, so let's go ahead and let's talk about a special type of voltaic cell. And that's one where I have gases involved. So let's say I have something where I have H plus going to H2. This is on the cathode side. And on the anode side, I have Mg going to Mg2 plus. Okay? Notice on the anode side, I could just have magnesium there because magnesium is a solid. But in this case, 2H plus is going to H2 gas. I can't have an electrode, which is a metal compound, a piece of metal. I can't have that made out of a gas. So what I need to do is sometimes I can have an inert electrode. That inert electrode is something that just allows electricity to flow. Right? So we need to bring in something else. And what we can bring in is something that is a good conductor, but not involved in the reaction. And so, for instance, we could use platinum and we can use gold, and this will allow the electrons to move through there. In the same way that electricity will flow through metals, but it won't flow through plastic or something else. Okay. All right, so these inert electrodes, they're not involved in the reaction, but they are important for the cell. And so what we do is we write them as basically after my cathode, I basically just put another line and then I put in that inert electrode. Okay? Now this inert electrode is basically a catalyst. Right? It's not part of the reaction, but it's required for it to occur. All right, so let's go on and let's just do some work with cell notation. All right, so let's say we have this. We have Mg solid, MgNO2 aqueous. And then we have H plus aqueous and H2 gas and platinum. All right, so that solid or that double line represents the salt bridge. So on the left-hand side, I have my anode. My anode is Mg, Mg2 plus. Okay. This is my half reaction, so I have Mg solid going to Mg2 plus. How does something go from 0 charge to 2 plus? It loses electrons. In this case, it loses 2 electrons. That's what oxidation is. All right, we have our cathode over here. Our cathode, we have H plus and we have H2. So notice how this means I have H plus going to H2. But notice that this isn't balanced. So I need to have 2H plus going to H2. And so how do I go from 2H plus to H2? I have to add in electrons. Okay? So this is what's happening at my anode. This is what's happening at my cathode. And my overall reaction is the sum of these two. My magnesium solid plus 2H plus going to magnesium 2 plus plus H2. This is gas. This is aqueous. This is aqueous. If you flip these two, it doesn't matter. If you flip these two, it doesn't matter, as long as I have reactants and products. Okay? This is my reaction. But notice I have that inert electrode. What do I do with that inert electrode? Because it's a catalyst, I just put that there. So platinum is involved as a catalyst in this reaction. Okay, so this is my reaction, and now I have to ask what's being oxidized. Well, oxidized involves losing electrons, so that means that magnesium is oxidized. What's being reduced? Well, my H plus is being reduced. Okay. All right, what is the anode made of? The anode is made of magnesium. It's always made of the solid, not of the aqueous, right? I can't have an electrode that's liquid or aqueous. And my cathode, well, my cathode's over here, but it's not going to be the H plus or the H2. It's going to be that platinum, that inert electrode that's needed for it. All right, so here it is on the screen. So this is just looking at cell notation. The cell notation is a shorthand way to show what's going on, right? If I were to draw out the apparatus, I'd have magnesium over here, and I'd have platinum over here. This is platinum. This is my magnesium. I'd have a solution containing magnesium, 2+. I'd have a solution here that has H+. I'd have a salt bridge going between them, and I'd have a wire going between them. And so electrons would go this way, and my H+ would form H2 gas. Meanwhile, on this side, my magnesium would form Mg2+. All right, so that is an example. Why don't you do a example on this cell notation? Copper solid going to copper 2+, and then platinum 2+ going to platinum. All right, so figure out what's being oxidized, reduced, what the anode is, what the cathode is, and the overall chemical reaction. Okay, so what's the point of voltaic cells? The point of voltaic cells is to create voltage. And we talked about that cell potential. That cell potential tells us how much voltage I'm going to get out of it, right? So if I were to make a battery or some cell that has copper and platinum, I want to know how much voltage I can get out of it. And this is our cell potential. Now, under standard conditions, we have the standard cell potential. And this allows us to basically tabulate it, because we can say, hey, under these standardized conditions, how much voltage do we get? Right. Okay, now, cell potential depends on the metals involved. For instance, the first one we talked about with copper and silver, we get 0.46 volts. If it's copper and platinum, I get 0.86 volts. If I add copper and copper, I'd actually get 0 volts. The reason being is, in this case, copper is going to copper 2+, and here copper 2+ is going to copper, so no real reaction is occurring. Okay, so it's handy to go ahead and compare a lot of these electrodes over here to some kind of standard. And the standard we use is something called the standard hydrogen electrode. Okay? Standard hydrogen electrode is one where we have H2 gas forming H+ aqueous. And so we use this as our anode, and we hook up, let's say, silver as our cathode, and we see what happens. So for instance, let's say I had a cell where over here I have my She, standard hydrogen electrode, as my anode, and over here I have copper as my cathode. And I go ahead and I see what the voltage is. Right? I get a cell potential here of 0.34. I could do the same thing but switch out the copper for lead, and I get a different cell potential. Okay, in this case, it'd be negative 0.126 volts. Well, what I do then is I say these values are my standard reduction potential. The standard reduction potential is the cell potential for reduction, right? Because that's what's happening in both these cases, versus that standard. Okay, so I can see that, oh, for copper, it's 0.34. For lead, it's negative 0.126. And so because I'm ranking these versus the same standard, right, I can say, okay, I can put these in a table. In the same way, when you have a film critic, they'll say out of 5 stars, right? So if they say 4 stars and they say out of 5 stars, then I can tell something. But if it's 4 stars out of 4 stars, it's something different, right? So I have some standard in order to rank things. All right, so for example, we can have a bunch of reduction reactions. Okay, so I have copper 2 plus going to copper. I have tin 4 plus going to tin 2 plus. I have nickel 2 plus going to nickel. All of these are reduction because they're all gaining electrons. Okay, these are from your book, by the way. And I have different cell potentials over here. Okay, or sorry, standard potentials over here. Notice how they vary from some are positive, some are negative. For my standard, remember my standard was H2 and H plus. This has a cell or a standard reduction potential of 0, right? Because it's comparing it to itself. All right. The more positive the standard reduction potential, the more likely it is to be reduced. Okay? This makes sense. The higher the reduction potential, that means it gets reduced. In the same way, bless me. In the same way, if we're talking about the NBA or the NFL draft, they're going to go ahead and they're going to draft the person with the most potential, right? This is Zion Williamson from last year. They looked at him and they said, he's a huge guy. He knows what he's doing on the basketball court. He has the potential to be a great athlete, great basketball player. So what do? We have him do basketball, right? If something has a high reduction potential, we have it be reduced, okay? Things with a less reduction potential, these aren't likely to be reduced, okay? If here I was, and here's Zion Williamson, they're going to see him as having way more potential than me, and they're actually going to draft him, right? In fact, David Silver here, the commissioner, he has more potential than I do too. So he'd probably get drafted before me, all right? So let's put this into practice. Let's say we have a cell, a voltaic cell, made up of a copper electrode and a cobalt electrode. Okay? So here's copper 2 plus going to copper. Here's cobalt 2 plus going to cobalt. Okay? These are two reduction reactions. But I can't have two reduction reactions occurring, right? Remember, we call it redox because we have to have reduction and oxidation. Okay? So one of these will be reduced and one will be oxidized. Which one gets reduced? Well, the one with the most potential. So my copper 2 plus, that's what's going to be reduced. So I'm going to have copper 2 plus 2 electrons going to form copper. Well, what happens to the cobalt? Well, that means it must be oxidized. And so if it gets oxidized, that means we have to flip it. It has to go cobalt solid going to cobalt 2 plus 2 electrons. The copper is my cathode. The cobalt, that's my anode. Okay? The difference between the two, that's my cell potential. Okay, so how would I write this in cell notation? I'd have cobalt 2 plus going to cobalt. Why? Because I always start off with my anode. Then I show the salt bridge. Then I have the cathode. And at the cathode, I have copper 2 plus going to copper. Oops, notice I messed this up. I forgot to account for the fact that this is oxidation. So it wouldn't be copper 2 plus going to copper, or sorry, cobalt 2 plus going to cobalt. It'd be cobalt going to cobalt 2 plus. Okay, this would be my cell notation. Okay, let's go ahead and let's figure out what the cell potential would be for this reaction. Oops, I got a new marker and it stains. It doesn't want to get erased. Oy. All right, so I have copper 2 plus going to copper. And I have cobalt going to cobalt 2 plus. Okay, so what we do is if we want to know the cell potential, we go ahead and notice at the top of the screen, I take the reduction potential of the cathode, and I subtract off the cell potential or the reduction potential of the anode. So if I tell you that the copper, that's my cathode, it's going to be 0.34 minus that of the anode, which is negative 0.28. So this is going to get me a cell potential of 0.62 volts. Okay? Notice at the very top I say, hey, you can just take the difference between the two and make it positive, right? Let's say I did this in the opposite way, and I did negative 0.28 minus 0.34. Well, here I would get negative 0.62. So if I take the absolute value of this, I'd still get 0.62 volts. Okay, either way works. Okay, here it is on the screen. And if I wanted to go ahead and I wanted to know the reaction for this, what would I do? I just put together these two half reactions, where here I have reduction and here I have oxidation. Okay. And they come together to give me this. Notice the electrons cancel out. Why do the electrons cancel out? Because I have 2 electrons as a reactant in the first one, 2 as a product in the second. Okay. This means that if I were to have a voltaic cell that had copper on one side, cobalt on the other side, I would get 0.62 volts. Okay. All right, this is problem 26b. In this one, you want to figure out the cell potential for this reaction. Oops, sorry. So you want to figure out what's our anode, what's our cathode, and figure out that cell potential. And then we have video problem 26C. 26C basically tells you we have a nickel electrode in a nickel 2 plus solution and a tin electrode in a tin 2 plus. So it asks for what's reduced, what's oxidized, what's the overall chemical reaction, and what the E cell is. Okay? Notice, by the way, that there are 2 tins there. Which one am I going to use? Well, I have solid tin, and I have 2 and 2 plus, so the reaction I use and the reduction potential I use should be for those 2 compounds. All right, so that is it for cell potential. Now we're going to talk briefly about applications of electrochemistry. So this is how we get electrical energy, right? A battery, if let's say it's called zinc carbon, what that means is that one of the electrodes is made out of zinc and the other is made out of carbon. So here's a carbon rod, here's zinc on the outside, and then in between we have some separator that acts as the salt bridge. Okay? And so what do we have? We have here where we can put this battery into some kind of circuit and we can get electricity flowing between it. Okay, actually, electricity will flow this way from the negative to the positive. We can also have something more advanced. We could have nickel cadmium. These are what are called rechargeable. And this, you can notice it has many different electrodes, right? This is called the jelly roll. Well, you have a positive, a cathode and an anode, and then another cathode, another anode, etc. Okay? And so the whole thing is that this reaction produces voltage. But in a rechargeable battery, what I can do is, once it's done, I can put it back in to the charger, and the charger puts voltage in, and so that basically reverses the reaction. And then I'm back to where I started, and then I can use it again. We also have batteries in our car, right? That's a lead acid battery. It has lead, and then it has H2SO4 in there. Batteries, if you ever picked up a car battery, you can see it sloshes around, and it has a port where you can add water to it, right? Because that water acts to move those electrons around. Okay? All right, so we talked about standard cell potential, where we have an anode and we have a cathode. These have a positive cell potential. What that means is they will produce voltage spontaneously. If basically I close the circuit and I put a wire between the anode and the cathode, I get electricity flowing. Let's say I had the opposite, going from cathode to anode. This is not spontaneous. I need to put energy or voltage into there in order for this to occur. This would have a negative cell potential. All right, now it turns out, and this is an equation you don't necessarily need to know, that the work associated with voltaic cells is equal to the cell potential times the charge. And the charge is dependent on the number of moles of electrons and some constant F. Okay, that's Faraday's constant. That's the charge of 1 mole of electrons. So, the electrical work associated with a voltaic cell is equal to negative N times F times that cell potential. Well, it turns out this is also equal to Gibbs free energy. And so I have this equation here, delta G equals negative NF E cell, the cell potential. And what this says is, remember what we said, anode going to cathode, that's spontaneous. Okay? So a positive E cell gets me a negative delta G because of this negative. Right? So if I have a positive cell potential, I end up with a spontaneous reaction. The opposite, where this is negative, gives me a positive delta G. Right? This would be non-spontaneous. This is what we call an electrolytic cell, which is basically the opposite of a voltaic cell. All right, so we have this equation right here. And what this means is, remember, we have this equation, and then last time, when we were talking about K, which is our equilibrium constant, we related that to delta G. Okay? And we can also relate E, the cell potential, to that equilibrium constant. So what this means is, we have delta G that we talked about in thermo at the very beginning of the quarter. We have K, which is equilibrium, and we have cell potential, which we talked about in this lesson on electrochemistry. Everything we've talked about in this class is related. Okay? Now, you're not going to have to relate delta G to cell potential or cell potential to equilibrium. I just wanted to show that everything we talked about is related. And that is why it's important to, over the summer, if you want to go into OChem and you want to excel, study some of this, because this isn't just all going away. All right, so that is it for lesson 26, the last lesson we're going to do this quarter. Okay, we talked about voltaic cells, where we have an anode and a cathode, and we have a wire between them, and that wire allows for electrons to flow, and that's how we get electricity. We can calculate the voltage associated with this based on the standard reduction potentials. Okay, the higher the standard reduction potential, the more likely it is to be reduced. So tin 4 plus will be reduced before H plus, will be reduced before lead 2 plus, and before tin 2 plus. Okay? And then we talked about this connection between them all. Okay? You're not going to need this for the test, but all it goes ahead is it just shows that chemistry is related. All right, so that is it for lesson 26. Remember, homework for this is due on June 8th. On that same day, you have a quiz during our normal Zoom hours, and I will post a review of the entire quarter. It will mainly focus on the new material, but I'll have some stuff on the previous tests. We have SI from 4 to 5 on June 8th. I have office hours at the normal Zoom link. I don't have it up here, but it's on the page. You've seen it. From 11 to 1 p.m. on June 9th. I also have those same office hours on June 10th. And then the final is from 2 to 4 p.m. via Sapling. Okay? It will be 60 points and it will be 90 minutes. I'm going to actually right after this, I'm going to make a video and I'm going to post that so it'll give you information on both the quiz and the final. All right, that's it for Chem 216. These are strange times and they're getting stranger. Just be safe, be smart, focus on your family, focus on your own well-being, focus on community. All right, with that, bye-bye.